Hello and welcome to the screencast on scientific notation, SI prefixes and units. I'm Mrs. Willie and let's get started. SI units are specific quantities or amounts used for measuring. Scientists use the System International or SI, and any unit in this system is an SI unit. Some of you may have heard of the meter and some other base units. In the metric system, they are all based on the number 10 and they are a part of the SI. So here in the United States, we use what is called the imperial system. So you're used to seeing recipes like I have on my screen where they call for 1.5 cups or a half a teaspoon or a stick of butter. Most of the world otherwise uses the metric system. So in this recipe that I have found for you, you can also see where they have the metric measurements. So they would say grams of sugar or grams of flour. Notice that when we're talking about counting items, so in this case, the recipe calls for 1 egg. There is no differentiation. That's a counted number, not a measured number. So 1 egg counted in other parts of the world is the same as 1 egg counted here in the United States. So the SI units have base units and what are called derived units, but I will get into those in just a minute. Right now we're going to focus on base units. The definitions of these base units are defined by the General Conference on Weights and Measures. And if you would like to know more about them, please visit your text. They are defined by fundamental constants of the universe. And you will not need to memorize those or know those for a test. And they would probably be more important going into physics than they really are here in chemistry. So we're just going to focus on what the base units are and the units that we use in those. So the base unit for length in the SI system is meter. The base unit for mass is the kilogram. And I know this is tricky because we're used to using grams, and we will switch to that when we're talking about practice problems and the practicality of what we do in the lab. But remember, these are defined by constants in the universe. So we're going to leave the base unit here, the kilogram. For time, the base unit is second. For temperature, the base unit is Kelvin. And we will talk a lot more about that throughout the course of our year. And then number of particles, the base unit is the mole. And some of you may have not heard of the mole, and that is perfectly okay. We introduced it a little bit in the previous 2 screencasts. Remember, the mole could be number of particles, so a specific number of ions or a specific number of atoms or a specific number of formula units or a specific number of molecules. That mole can mean any one of those, just depends on the situation that you're speaking about. So let's move on to derived units. So derived means to take from, and for our purposes, derived units and the scientific concepts are used in calculations based on the base units. So an example would be area. For area, you're taking 2 length measurements and multiplying them by each other, getting the derived unit of meters squared. For volume, you are taking 3 length measurements and multiplying them by each other. So you have meters cubed. And for density, you have a mass over a volume, and these units can vary based off of whatever the measurements were that were taken. In this case, using the base units of kilogram and length. I would like to take note here at the bottom. So it is also common in North America to use liters to express the volume of the liquid in the container, even though liters is really used to express the capacity of the container to hold it. So for example, here in North America, we would say that I had 3 liters of liquid when in other parts of the world, they would be referring to that volume as the size of the container. So if I had 3 liters of liquid in a 5-liter container in other parts of the world, they would say 5 liters in relation to the size of the container, not the measurement itself. Now let's talk about a more conventional way to think about these instead of using universal constants. So for our class and for our purposes, mass is the amount of matter contained in the sample. Volume is the amount of space that sample occupies. Temperature is a measure of the average kinetic energy of the molecules in the matter. Doesn't necessarily have to be molecules. This could be formula units, this could be ions, this could be atoms. And density is the ratio of mass to volume. So I've given you an image here that I thought is really helpful to help you remember what the formula for density. So it's I heart density. When you draw the heart, you just draw the line in half and it would be mass divided by volume. So you will always remember the formula for density. This is an easier way to remember what these concepts mean for our class purposes. So conversions that you will need to know. What this means is you will need to memorize these. These will not be given to you on checks for understanding in class. So you need to spend the time memorizing these metric prefixes or these SI prefixes. So kilo, centi, milli, micro, nano, and pico. This can be found in your course electronic textbook. So please visit there as well for an extended list of SI conversions that can help you to the imperial system, not necessarily just these that you have to memorize. A helpful way to memorize this, from what I hear, is King Henry drank chocolate milk, to help you remember the order in which the SI prefixes come. So you have kilo, hepta, deca. Then we have what is missing here is deci. Then you have centi, milli, micro, nano, and pico. So our base units for our use in class, not necessarily the base units from SI. Says, remember I talked about they use the kilogram as their base unit. We are going to most likely, and for more purposes, use the the gram as our base unit. So let's just look at some of these conversions. So if I had to convert from kilograms to grams, for every base unit here, so we'll say this is the gram, I have 10 to the third kilograms. So this means that I'm going to have 1,000 grams for every 1 kilogram, because kilograms are larger than our base unit. So our next conversion would be centiliters to liters. So if I look to this to the right of the deci, or the decimal place, are the smaller than the base unit. So this time our number should be smaller than our original number. So I'm going to have 1 centiliter. So then I need to go back 2 times. So that would be 1, 2. So that means I would have 0.01. And that should be liters, not grams. Then you have 1 microsecond. If you look to the top here, there are 10 to the 6th microseconds for every 1 second, because that would be our base unit here. My answer would be 1 over 10 to the 6th, or 10 to the minus 6 seconds. If I have 1 picomole is equal to how many or X moles, remember now our base unit would be moles. So I look up here, the pico is 10 to the 12th. So I have 10 to the 12th pico for every 1 mole. So again, 1 over 10 to the 12th or 10 to the minus 12 moles. So you may be wondering, why do we use scientific notation? Well, in chemistry specifically, we are using scientific notation to express very large or very small numbers in an easy way because we are dealing with particles that are very, very small. And so you have large amounts of them when you're thinking about this in terms of base units. And your hand would become very, very tired, even though it's already going to come very, very tired from all of the practice we do. So you want to limit how long it takes for you to write those numbers. So scientific notation is a helpful way in dealing with making large numbers manageable to write and small numbers manageable to write. And it also helps you to determine what the significant figures are in that number. And we will discuss significant figures in the next screencast. So scientific notation is all numbers are expressed as the product of a significand. The significand is the whole number in the number that is expressed. It must be between 1 and 10. This is very, very, very important because if you see a number that is greater than 10, then it is incorrectly expressed and you will have to convert that to the correct significance. So for example, if I had 250 times 10 to the, let's say, 5th power, I would have to move that decimal point so that it was between 1 and 10. And if I move that to the left, then that means this number would get larger. So then I would have 2.50 times 10 to the 7th. But it is very important that your significance stays between the numbers 1 and 10. In our example here, I kind of talked about it a little bit on the bottom, but so I want to take this ordinary notation, which is how this is expressed, and convert it into scientific notation. In order to do that, I'm going to move the decimal however many times so that I have the number between 1 and 10. Then you would count however many that is. 1, 2, 3, 4, 5, 6, 7, 8, 9 in this instance. And if I'm moving the decimal to the left, then my exponent will be positive. An example on the bottom is if I'm moving my decimal to the right. So again, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then my exponent will be negative. Some more examples on scientific notation and how it works and why we utilize it with the SI system. Remember, we talked about how the SI system is based with the number 10. So scientific notation is very helpful for us because it is also based on 10. So an example here would be 10 to the 1st power would be 10. Now, the tricky point here is if you had 10 to the 0 power, then this would actually mean 1. 10 to the 2nd, you take this and would multiply 10 times 10. So I take whatever number it is here on the base and multiply it by itself however many times in the exponent. So 10 times 10, my answer would be 100 in ordinary notation. If I had 10 cubed, then I would have to multiply 10 times itself 3 times, and I would have the number 1,000 in ordinary notation. So this works the same backwards, except instead of the number being 10, you're going to have to multiply by 1/10, or in decimal terms, 0.1. So 10 to the minus first would equal 10 times 0.1, which would give you 0.1. 10 to the minus second would be 0.1 times 0.1, which equals 0.01. 10 to the negative third would be 0.1 3 times multiplied, which gives us 0.001. So some examples. 2 times 10 to the first would be 2 times 10 one time, which would equal 20. 2.62 times 10 to the second would be 2.62 times 10 times 10, which would equal 2.62 times 100, which would equal 262. Now let's do some using negative exponents. So you would have 5.30 times 0.1, which would equal 0.530. Then you would have 8.1 times 0.1 2 times, because it is 10 to the negative 2. This would equal 0.081. So now let's look at the opposite. I have a number in ordinary notation, and I need to write that number in scientific notation. So rewrite the numerical quantity so it lies between the numbers 1 and 10. Remember that significand can only be between 1 and 10. To do this, you would count the places that the decimal was moved to obtain this number. So our first example down at the bottom would have a decimal point, even though it is not there, at the end of the number. And I want to make this between 1 and 10, so I'm going to move the decimal between the 8 and the 1. So I'd go 1, 2, 3 times. If it has to be moved to the left, which we did, then I know that it's going to have a positive integer. So I would rewrite that as 8.162 times 10 to the 1, 2, 3. In our second example down here, you want to have your significand again between 1 and 10. So 0.054. I'm going to move the decimal 1 2 times, and I'm moving the decimal point to the right, so my integer, my exponent, has to be negative. So it would be 5.4 times 10 to the minus second. So now let's talk about what happens when we are having to do mathematical operations with scientific notation. We're going to start with addition and subtraction. So if we're going to be adding or subtracting numbers that are in scientific notation, then the exponents must be equal. So for my first example here, I have two numbers in scientific notation, and I first look at their exponents. Their exponents are not equal, so I must convert one of the numbers so that its exponent is the same as the other. What's important to remember here is it does not matter which number that you choose. You can choose either number to match. It does not matter. You should still get the same answer irregardless of which number that you choose. So I'm just going to choose the first number, and we want it to match the exponent here of 2. So I want to make this number smaller, so I'm going to move the decimal to the right. So I would rewrite this as 54 times 10 to the second plus 6 times 10 to the second. now I can remove both of the significans and just add them. So it would become 54 plus 6.0. So this equals 60 times 10 to the second, and then I would need to change this because this is not between 1 and 10. I would need to move it the decimal point back, so then this becomes 6.0 times 10 to the third as my final answer. So had I chosen to do this the other way, then it would have to change the second number in this because we want those exponents to match. So I would leave 5.4 times 10 to the third the same, and then I would change the second, and we need to move the decimal place to the left because we want the exponent to be larger. So this becomes 0.60 times 10 to the third. Then I would add those two significance together just like I did in the other. So this would become 5.4 plus 0.60 times 10 to the third. So my final answer here would be 6.0 times 10 to the third because lowest number of decimal places, and you'll learn that in our next lesson on significant figures, but they match. So you can see it does not matter which one you choose to change. You should end up with the same answer either way. So now let's do subtraction. Same premise. You need to make sure that the exponents are identical before you do the actual subtraction. So let's move the first one just like we did in the other. So this becomes 13 times 10 to the fifth minus 2.1 times 10 to the fifth. So then I would take 13 minus 2.1 times 10 to the fifth, which gives me 10.9 times 10 to the fifth. And just like in our first example, our significand is not between 1 and 10. So we need to move the decimal place again. So this would become 1.09 times 10 to the sixth. And if I'm really looking at, significant figures, only one decimal place in these, or two significant figures, my final answer would be 1.1 times 10 to the sixth. So now let's look at what happens when you multiply or divide, scientific notation. If I'm going to be using multiplication, then I add the exponents. So first example would be 3 times 2, and then I would take the 4 plus the 2 in my exponents because I have a 4 and I have a 2 here. So 3 times 2 is 6 times now 10 to the sixth. A lot easier to use multiplication in scientific notation than addition or subtraction. So in division, it's just the opposite. So we added the exponents for multiplication, and division will subtract the exponents. So in this case, I will have 3 divided by 2 times 10 to 4 minus 2. 3 divided by 2 would equal 1.5 times 10 to the second power. Thank you for watching my screencast, and hope to see you again.